So, now we make a shift to how we can use that to actually provide the interval that I used in the beginning. Here it is. That's the interval I showed you on slide 1. Here it comes as a method. I gave you most of the arguments behind the method already now, most of the thinking. So here's the method. The method takes the observed mean plus minus the computed S divided by root n. You remember that 12 point something divided by, we'll see it again. And then we take something which looks a bit odd there maybe, but it's not too bad. It's the point on the t distribution. I should actually go like this here. That makes it easier to say. Because most commonly, this formulation up here looks a bit odd, but it just opens up for that we can work with different levels of confidence, actually, in our construction of intervals. There is not only, actually, that's the challenge, there is not only one interval. There are, in fact, different intervals depending on how certain, how confident you want to be, right? The most commonly chosen level of confidence globally is the 5%. Or I should say, maybe here, it's more correct actually to say when we put it like this, is the 95% confidence. I should say it like that. And we'll get back to this alpha 5% in a couple of weeks, not now. But the alpha, this is just the way it's being put. It looks a bit awkward actually with all that. But it's just to say this general formula looks like this if we make a choice of the most commonly level of confidence. That is, the confidence where I have 95% within and only 5% in the tails, 2.5%. That's the commonly chosen level of confidence. Then, this t number called t.0975 is the number having 2.5% out here. 2.5. And then this is a symmetric t distribution, very clearly shown by me. I've spent, let me count, 84, that is 31 point something years practicing doing those nice sketches of normal and t distributions. That's as far as I got in those 31 years. So I decided not to go for anything where that's going to be important for my career, that I can do some nice drawing. So I chose a career where there's a computer to help me. But hey, here it is. These are my sketch. That's how they look. This is the same number, just with a minus, right? It's symmetric. Here we have a 0 in the middle. So this is minus t and plus t here, right? It's symmetric just like the standard normal. The t distribution is very much like the standard normal in our minds, but sometimes it's just a bit wider. That's how we can think about it. So we have this plus minus approximately 2 standard deviation, but not exactly 2. We take the 2 from the t distribution. Now this plus minus 2 only go together with the 95% confidence, right? If I want 99% confidence, it's not plus minus 2 anymore. It's maybe more like 3 or anything. So the plus minus 2 is just, like in the standard normal, goes with the 95% confidence, right? So, the student height, I showed you the result already. Here is how you can get the t quantiles from R, because of course they are there. This is new, you see this now. We write qt for the quantile version of the t distribution. I put the 0.975, that's the quantile I'm interested in, to construct this interval. And then I have to tell it which t distribution to use, because there are many different of those. Should we try? Want to make a point here? Let's try. This one, 2.26, that's the generalized 2 that I showed you on my initial slide. What happens? Let's just make that thought experiment. What happens, let's just emphasize it a bit more. What happened if I had 1,000 observations, right? Then the theory would tell me to use the t-distribution with 999 degrees of freedom. Let's see what happens. Do you recognize this number? If there is one quantile in this course, you should remember, or put differently, the quantile on the top of the top 3 list that you should remember when you leave this course is this quantile coming here. The standard normal quantile, the standard normal 95%, or I should say, formally speaking, the 97.5% quantile giving us the two-tailed 95% confidence area, right? That is 1.96 in practice too, but exactly 1.96. And my point is, look at that. If we have many observations, the t-distribution becomes closer and closer to the normal. So with 1,000 observations, I can at least up to 2 decimal points not distinguish using the normal and using the t, right? That tells us something. So, let's see. Get a bit excited here because this is good stuff. Really important stuff for your careers to know about this. So here is the computations done that I showed you on the first slide. We use this t, we plug in the s, we plug in the mean, we plug in the n. It's a simple formula to play around with ourselves, and we extract the quantile and we compute the formula. The interval tells us that if I take my 95% confidence interval, it's between 170 and 187. Didn't that nicely match the histogram that when I did my initial playing around of things? And that's actually more or less the same thing. Well, what happens, just to make this example, what happens if I would have a higher degree of confidence? 95% is not enough for me. I want to be more confident. Why should I live with this 5% chance of not being there? Whatever that means. We'll get back to that. Then I could take a 99%. I plug in the 99.5 here because that is to get the point of the t-distribution. Oh, that was a nice one. Where I have a 0.5% in each to get the 99% like that, right? So I find this number, this one, is the one with 99.5% to the left of it. The 99 and the remaining half in the left tail, right? To get the right number. And as I told you, then we might end up somewhere else than the 2. Beyond 3. So we have to get this feeling into our stomach. If we want to become more confident, the price is a larger interval, right? Makes sense, even though you might have thought differently, but it makes sense if you start thinking about it. If you want an interval computation that makes you more certain that your true value is in the interval, you have to widen the interval a little bit to get more certainty, to get more confidence in your statement. And then we get, if we go up to 99%, we get the rest of us into the interval also, just barely. At least some of us, not our basket guy, he did not come in, and also not Nelson Mandela, I remember. He was also in our survey a few weeks ago. He was 140 centimeters, I believe. That was actually Nelson Mandela. I'm not, this is one of you guys trying to do some jokes, right? It's not something I make up. And I thought it was pretty funny when I saw it, actually. So thank you for that. And then, to the good news, although for you maybe it's not good news, because I demand of you that you can handle both, right? You can handle the formula for how to compute it manually. You know what the formula consists of, And you should also know this beauty that I'm telling you now, that there is an R function that can do it all for us, just like that. And it can do much more. Some of the stuff we'll get back to next week and the next week again. It can do that also. The function is called t.test. We just plug in the vector of data, so the row of data or whatever, we plug that in, and basically it computes different things for us. Today we can recognize DF9. We can recognize because I specifically ask for the 99%. If I don't, it will find the 95% for me. But here I specifically ask for the 99% confidence interval, and it will give it to me. It would also tell me what the sample mean is, 178. It doesn't actually show the variance there, but we could find that ourselves. By the way, did I remember to remind you? I don't think I did, but I think you realized that some of these things are, of course, very important for your project work. Now that we start doing real statistics, not surprisingly, the first tools that I'm going to give you these weeks before you have to do your project are, of course, the tools you're going to use in your project. That is pretty obvious, so it's a good opportunity to listen in carefully.